Alright, silly people, here's the situation. We're going to be using a variation on the trapezoidal rule to do an integral that we've done a couple of times before. So this is the trapezoidal rule, just this order h term. But then you also can include an h squared over 12 term that involves derivatives to do the integral, and it's ever so slightly more accurate. So we're just going to get right into it. We're going to define the integrand as always. We're going to be integrating x to the fourth minus 2x plus 1. So I'm going to define that as f of x. It's going to return x to the fourth minus 2 times x plus 1. Right? And then we can also define the derivative. That's going to be a thing that we need. Just by doing the central difference version of the definition of the derivative. So that's going to be f of, we need to define a h term to like vary the the derivative. So I'm just going to call that capital H, and the book suggests 1 e to the minus 5. So 10 to the minus 5 is good enough. And then that's going to be x plus capital H over 2, and then minus f of x minus capital H over 2, and then all divided by capital H. Right, and then we can start doing the trapezoidal rule. The lower bound is 0, the upper bound is 2, 0.0. We want to do 10 slices according to the problem statement, and that's kind of really silly, and I'll tell you in a second. H is going to be b minus a over n, and then we will start making the s, which is going to be the result of our integral. I'm just going to use this formula directly. So that's going to be h times, in parentheses, 0.5 times f of a plus 0.5 times f of b, and then plus the h squared stuff right now. So in parentheses, h squared times f prime of a, so df dx of a, minus df dx of b all over 12. Yeah? Okay. And then we can just do a for loop k in range n and just add on to the integral h times f of a plus k times h pretty simply. And then after that we can print out the result of the integral like that. So we can run this. It's going to give us 4.6. The result of the integral, if you do it analytically, is 4.4. Doing it with 10 slices is not going to give you a good result either way. If I up the n to 100, it automatically gets way better. And then even if you go to 1,000, like now you're really killing it. But to talk about the 10 slices thing, with the derivative measure added on to the calculation, you're getting 4.6. If you take that away and just have the trapezoidal rule, you're getting something like 4.7. So yeah, the h squared term adds on like a 0.1 like difference to the accuracy. So I guess it is slightly more accurate. And we can also observe what it looks like at the n equals 100. This is with the derivative term. You get 4.41, and then without the derivative term, you get 4.42. It's a very minute difference, right? And so also it asks why it's not much used in practice. Probably because talking about doing a integral, the first thing that comes to mind is not doing the derivative of whatever you're trying to do the integral of. I don't know, that probably doesn't cross people's minds very often. So, yeah.